This video is a supplementary learning material to accompany the self-learning module titled Ionic and Covalent Bonding, together with Teacher Jackie and Teacher Den.
Hi there! How are you? It's nice to see you back. We're in the last part of the 3-part video series, and like you, I'm excited to find the answer to our hanging question in part 2 of this video. So what are we waiting for? Let's start the ball rolling. Remember the properties that you observed during the activity? We are now going to discuss those properties. Let's start with the appearances of our samples, particularly their physical state at room temperature. As you have observed, all our samples are solid at room temperature. What makes them solid at room temperature? To explain this, let's recall the physical states of substances that you have learned in grade 8.
Remember that the states of matter differ in the distance and motion of the particles. Furthermore, the distance between particles depends on the strength of attraction between them. Let's see how that works in this model of physical states of matter. Among the three, the solid state has its particles closest to each other, which means solid substances, in general, exhibit the strongest attraction between its particles. But what facilitates the strong attraction of particles in solids? What keeps the particles together tightly enough even if the particles in a solid substance vibrate in place? Let's look at the bonds of our sample compounds. Think about the formula unit of NaCl. Each unit has a positive ion and a negative ion, right? What do you think will happen if several units of NaCl are near each other? Just like how opposite poles of the magnet bar stay attracted to one another, the oppositely charged ions would want to stay packed together due to the super strong attraction between them. And we know that matter composed of atoms or group of atoms that are very close to each other exists as solid.
Now, how about covalent compounds? What facilitates the strong attraction of particles in solid covalent compounds? How exactly does attraction affect the physical states of covalent compounds? Since the polarity of covalent bonds varies, the polarity of molecules also varies. This affects the strength of attraction between molecules, which in turn affects the state at which the molecular substance may assume at room temperature.
In polar molecules, partial charges are present. These will facilitate attraction between polar molecules. And if the attraction is strong enough, some polar molecules, for instance sucrose, can keep the molecules close to each other. That is why at room temperature, sugar, which is made up of sucrose molecules, exists as solid.
On the other hand, non-polar molecules are less likely to attract one another because they do not have partial charges. Examples of these are oxygen and nitrogen in the air that we breathe. Since almost zero attraction exists among their molecules, or the attractive forces between them are negligible, oxygen and nitrogen move freely as gases, keeping the distances between particles far apart. But wait! We've mentioned earlier that octadecane in candle wax is a nonpolar molecule. This means that when a molecule is nonpolar, it does not mean that it is automatically a gas, just like octadecane, which is solid. But how come it is solid at room temperature?
Octadecane is a relatively long molecule. Again, remember that the states of matter are described in terms of the distance between the particles. The distance between the particles is affected by their motion, and the size of a molecule affects that motion. The bigger the molecule, the slower it can move. This is one of the reasons why a large molecule like octadecane is close to each other. And when particles are close to one another, we describe the substance as solid.
Another reason why octadecane is solid at room temperature is its linear structure. This allows molecules of this compound to easily stack on one another, leaving smaller gaps in between them, just how the particles are arranged in a solid substance. Let's now talk about the melting point and boiling point of compounds. Do you remember the physical changes that occur during melting? How about boiling? During melting, solid is heated and it changes to liquid. If we add more heat to this liquid, it will boil. Thus, it will turn to gas. But what dictates the temperature at which substances will melt or boil? The temperature at which melting or boiling will occur still depends on the strength of attraction between the particles of a substance. Here's a question. Which do you think requires more heat to melt? A sample whose particles are strongly attracted together, or a sample whose particles are weakly attracted together? If particles are strongly attracted together, it will require a relatively high amount of heat to weaken the strong attraction, which means higher melting point. On the other hand, the one with weaker attraction between particles will require less heat to melt. In short, the stronger the attraction of particles in a substance, the more difficult it is to weaken it. Thus, the substance will require higher temperature in melting and in boiling. Among our three compounds from the activity, sodium chloride has the highest melting point and boiling point. That is expected because it is very difficult to weaken the very strong attractions among the ions of sodium chloride.
Between octadecane and sucrose, sucrose has a higher melting point. Again, the polarity of their molecules explains the difference in their melting points. Sucrose molecules are polar, while octadecane molecules are nonpolar. Between the two, sucrose molecules have stronger attraction between them due to their partial charges. Thus, it requires more heat to melt.
You will find a trend here that ionic bonds are the strongest while the nonpolar covalent bonds are the weakest. But this is just a general trend. This may not always be the case. What's more important for you to remember here, though, is that when you find a substance with high melting point or boiling point, you may infer now that the bonds between their particles are very strong, and vice versa. In terms of hardness, ionic compounds are relatively hard due to the strong attraction between oppositely charged ions. Also, they are generally brittle. Why is that so? Here's a representation showing how this breaking occurs. When an external force is applied on the solid ionic compound, layers of ions can slip past another under stress. This can cause similar ions with the same charge to get close to one another. Positive ions get close to other positive ions, while negative ions get close to other negative ions. This results in repulsion, which then causes the ionic crystal to break, thus brittle. How about covalent compounds? Similar to their physical states, melting point and boiling point, covalent compounds also vary in terms of hardness. Now, let's move on to solubility. In the activity, we saw that mixing salt with water gives a solution. The ionic compound sodium chloride is soluble in water but not in oil. This is true for many ionic compounds. But how do we explain this property? We need to check the polarity of the liquids. A water molecule has a partial positive charge and a partial negative charge. so we know it is a polar molecule. On the other hand, the main compound in oil, palmitic acid, is a non-polar molecule. Now, remember that sodium chloride is made of ions. These are atoms with full positive charge and full negative charge. What do you think happens at the atomic or molecular level if a sample of sodium chloride is mixed with water, which is made of polar molecules? There will be attraction between the ions and the water molecules. When an ionic compound is mixed with water, the negatively charged ions or anions are strongly attracted to the partial positive end of the water molecules. Likewise, the positively charged ions or cations are strongly attracted to the partial negative end of the water molecules. This is why table salt, a sample made of the ionic compound sodium chloride, is easily soluble in water. Now, what about table salt in oil? Why is it not soluble in oil? Remember that palmitic acid, the main compound in oil, is a nonpolar molecule. Would you expect this nonpolar molecule to form attractions with the ions of sodium chloride? Unlike with water, palmitic acid has a tiny polar part, but its properties are overwhelmed by the large nonpolar part. This is the reason why salt does not dissolve in oil. This is also the reason why oil and water create two separate layers when you try to mix them together. Oil is nonpolar. It has negligible partial charges that can create strong attractions with the partial charges of the polar water molecules. Based on that, we can say that polar molecules are not soluble in nonpolar solvent. By the same principle, ionic compounds and polar compounds generally do not dissolve in oil, but they dissolve in water. With this, an empirical rule was established. We commonly use the phrase like dissolves like to summarize this rule. This means that polar solutes dissolve in polar solvent, while nonpolar solutes dissolve in nonpolar solvent. We have seen those in the activity. We saw that table sugar with its polar sucrose molecules dissolve in the polar solvent water. However, candle wax with its nonpolar octadecane molecules did not dissolve in the polar solvent water. We also saw in the activity that the candle wax did not dissolve in oil. The candle wax remained solid upon mixing with cooking oil. However, if we were to mix molten candle wax with cooking oil, the two would surely dissolve one another because they are both nonpolar compounds. We will now discuss our last physical property, electrical conductivity. In order for a substance to conduct electricity, free flow of charged particles, such as ions, is necessary. In our activity from part 1 of this video series, only the solution made from dissolving salt in distilled water allowed this free flow of charged particles. That is also the reason why it was the only mixture that was able to conduct electricity. But do you know why there is a free flow of charged particles in the salt solution? Remember that the ions, charged particles, of sodium chloride form strong attractions with the water molecules. That means that the sodium and chloride ions are flowing freely in water. That's why the solution conducts electricity. Sugar solution and wax in water mixture do not contain these free-flowing ions. That is why both mixtures were not able to conduct electricity. While sugar and pure water, both polar covalent compounds, which means both possess partial charges, these charges only manifest as part of being in a molecule.
However, acids like hydrochloric acid and hydrofluoric acid behave differently. As acids, these compounds have hydrogen that easily separate from their molecules when dissolved in water, forming hydronium ions. That is why, when hydrogen chloride or hydrogen fluoride is dissolved in water, the resulting solution is able to conduct electricity.
Question. Earlier, we learned that ionic compounds can melt at very high temperatures. Now, if we have a molten ionic compound, say for example, sodium chloride in liquid state, do you think this will be able to conduct electricity? If an ionic compound is in liquid state, then its ions can easily slip past one another. This means that ions can flow easily. Therefore, molten ionic compounds also conduct electricity.
Oh, my mug is still here. Now, let's recall the previous scenes in part 1 of this video series. Do you remember the mug that I'm holding there? Yes, this mug. So, what do you say now about the mug? In this 3-part video series, you have learned that a mug is an example of ceramics, which have chemical bonds such as ionic and covalent bonds. You learned how these chemical bonds are formed.
You've also learned how different compounds can be recognized as ionic or covalent based on their properties such as point, hardness, polarity, and electrical conductivity.
Through your self-learning module in chemistry and this video, we hope that you were able to learn more about ionic and covalent bonding
and further develop your science inquiry skills in observing, hypothesizing, predicting, investigating, interpreting, and developing explanations based on evidence. Again, this is Teacher Jackie
and Teacher Dan. Thank you for watching and see you in our next chemistry video.